welcome to Computer Science IGCSE. Today we are going to look at the binary addition. In the last video we have talked about the conversions and hexadecimal, the basic stuffs we have actually look at those. Maybe many of you have actually known about these things, or maybe you are actually sitting for the next examination of October, November. So today we are going to look at the addition, adding together numbers, which is the binary addition, the process of adding number together. The two binary integers, whereas 128, 64, 128, 64, 32, 16, 8, 4, 2, 1. So these numbers are actually like the 8-bit binary number, and two binary numbers means 0 and 1. These are the two binary numbers which we are going to take it to the 8-bit system. There are 5 golden rules: 0 plus 1, 1 plus 1, 1 plus 0, 1 plus 0, which is this one is called the carry one number, and this one is the value. And over here, this number 1 plus 1 plus 1, which is 1, which is the carry number, and the one is this one, which is value. So there are 5 total things we must memorize this, so that we can actually easily do any binary addition. So let's move on to the thing where we are going to look at the binary addition. So as you can see, there is a binary addition I have done in exercise 1. Most of the time I actually do the exercise, but today I have actually done it for you. So let me discuss it about you over here. You can see that this number is 8 bits. This number is 8 bits. So 0 1 0 1 0 0 1 0. So these are the 8 bits number. And the second one is also 8 bit. And we are just now what we are doing, adding it. So how we are adding it? You see that 0 1 is 1. Why we have done 1? Because we have seen over here that 0 plus 1 is 1. So that's why we have done 0 plus 1 is 1. So as we have done 0 plus 1 is 1, then the second number, which is 1 plus 1, where 1 plus 1 is carry 1 and 0. So the 0 is the number which we are placing in the value, and the number we are carrying is the 1. That's the what we were actually telling, that 1 is the carry number and 0 is the value number. So after we carried the 1, we have taken it to the up, and then we are just adding it once again. So 1 and 1, these are the bigger number. 1 and 1 is bigger number, so 0 losses, so 0 goes the down. 1 plus 1, they are winning. 1 1 1 0, again 0 comes to the bottom. Over here again 1 plus 1, so 1 plus 1 is winning, so 0 is coming to the bottom. And then in the third section, you can see that after we goes again the 1, there is 2 zeros. Two zeros kills the 1, so that's why key number 1, the 1 goes down. This is the easiest way to actually get the thing. So 1 plus, then over here 1 plus 0 is 1. We have put this value, then 1. So this is the binary addition. Alright, so let's move on to the next one, is the overflow. Now in overflow, it's a very good important topic, but still in IGCSE or O level, this topic is actually now no more in the newest version, but in the older version. So as it's in older version, we're still gonna look at the some of this question, but in overflow, this overflow actually comes in with most of the maths, like in binary addition. This overflow comes in binary addition, and they will ask you to mention why the number is overflow. So when they will ask why the number is overflow, that time you have to actually answer these 2 points. That's why I have mentioned over here. Over here 3 points, but we must know about these 2 points. What is this 2 point says? When a number is larger than a register can store is generated or overflow. The register, in register we are actually doing is what? Register we are actually doing, we are putting those values, the 120, these values. So because I have actually like shown over in this photo, we are just putting this all these values in the register and then putting those binary values in the in form of those number. After we are adding it, or after we are actually like doing anything, that what it is coming is whereas it will come in overflow error, or it will come in a simple value number that we have shown in the last thing, like over here, like this it will come, or it will come with another bit, which bit will be called as the overflow. In this example we are actually looking at, this is the plus, we are adding it. So after adding it, what is coming is as there is another number, so that's why the number, because of that number, it's calling the overflow. So greater than 25. So what is the greater than 25? It's 256. So 1 is adding, that's why it's overflow. So as 1 is adding, which means in 8 bit, it will be the 9th bit. So this is the 9th bit. This is the 9th bit. 1. If we have told 1, 2, 3, 4, 5, 6, 7, 8, and this 9. This is the 9th bit. This is the 8th bit. So after 8 bit, when the value is greater, when it's in 8 bit, after the 8 bit, when 9 bits comes, this is the overflow error. When the number is greater than 225 and becomes 226, it is the overflow error. When the number is greater than 8 bit, then it is overflow error. So that's what it told over here, and in the last one over here it's told there that computer has a predefined limit, and it can store overflow error. Overflow is outside the limit generated. So outside the limit is generated. Outside the limit is generated. Like see this one, this is the overflow. That's why it is what? Outside the outside the value, outside the limit. Okay, this value is outside the register, so that's why it's generating an overflow error. Let's move on to the next one, which is logical shift. In logical shift, left or right bit most are lost, or over here lost or placed, whatever it is. Lost or placed, whatever it is. Okay, and filled with zeros. So logical shift can be left or can be right, and if it is left, then most of the significant bit is lost, or most of the significant bit is placed with zeros, whatever it is. And here it's already told that most or less significant bit is lost, and it's multiplied or divided by 0. It can be maybe a imaginary number like 0, 1. When it's logical shifted, it is divided when the logical shift is to the right, it's divided. If the logical shift is multiplied, then it will be in the left. So in overflow binary, binary shift doesn't come that much, but still we are going to look at it. Is overflow happens in when one is shifted. When 1 is shifted to the most significant bit on the left, the logical shift in one logical shift, this means this important data is lost, and as the important data is lost, this seriously changes the number value. Alright, so whatever it is, you must read it again. You must read to understand, so that you will be able to also go through the books, so that you will be able to get it. So I was doing some maths for you guys before I start the class, but later on found out that it would be easier if we solve it together. Wait a second. Alright, so let's move on to the topic, which is about exercise 1. We are going to look at 2 examples today. So in the first example, let's talk about a number which is basically um, okay, so it's 1 0 0 0 1 0 0 1 1 2 3 4 5 6 7 8. So over here we have talked about let's say two logical shifts to the right, two logical shift to the right. Okay, whatever I have mentioned in the last thing over here, I'm just going to review it once again in this maths. Let's go. Alright, the logical shift to the right. Now left. Let's move to the left first. Alright, so in logical shift, when we are moving to the left, that time we are taking the bit from the right and then placing it to the left. Alright, so let's go. So this bit will be lost, this bit will be replaced in here, right here. So what we are going to do is just put two zeros first. Let's change the color. Put two zeros first, like over here. We are just applying the thing, and then we are just going to put this number here, 1 and then 0, then 0 1 0 0 and 1 0. So 1 2 3 4 5 6 7 8. So oh my bad, not this number, my bad. 1 2 3 4 5 6 7 8. This is the number. Like after putting this number, that time we can put this two things over here. Alright. Now what we are going to do is just look at it, and once again look at it. So two zeros, 1 2 3 4 5 6 7 8. Over here the 8 numbers are there. We are just putting the zeros, applying the zeros over here, putting the zeros over here. Next zero, this, then this, and over here as there is two numbers, that time we are not going to put another two numbers because it's no more needed. So that's the number. So these are the number. These are the two numbers which this is the number. So this is the logical shift. And left. And one of the thing is interesting fact is that these were like in the last slide I have actually mentioned over there is the last point which was mentioned is that computer stores predefined values, and those values actually happens is that when error occurs, like when the logical shift is done, data is lost. So over here data is lost. How? This 1 and 0 are the datas, as I mentioned before. These 0 and 1 are the data. When this data are lost and replaced, like you see this data is replaced and put over here, and after I put, I can put these two numbers. What happens is that the data is lost, and as the data is lost and it's compressed, so that's why what happens here is that the data is no more a significant data, it's a lost data. So let's move on to this next math over here. Let's move on to the next math. Now we are going to do is the logical shift to the right. Okay, wait, what we can do is just the same thing. We can put this number and put left right over here. Okay, so let's do the right shift with this number. So in the left, as we have taken these two values from the left, okay, so we are just now going to put this value to the right. So in the right, what we have to do is just put 3 zeros over here. 1, 2, 3. And then what we're going to do? Then put this value 0, 1, 0, 0, 1. 1, 2, 3, 4, 5, 6, 7, 8. So this is the number. We're just doing it what? We are just putting these 3 values instead of these values. We are just putting 3 zeros, and then what we are doing? Taking this number over here, then taking this number, and then taking this number over here. So, oh wait. So sometimes you must actually look at the number properly so that you won't make a mistake. Alright, so these are the number. So these are the number which we have put. So, and this is the logical shift to the right. Here you go. We are done with this logical shift. Let's move on to the next one. Just do 2 or 3 times maths, then you'll be able to actually like easily understand. Now we are just going to do 2x complement. Over there is no theory about 2x complement, just to do maths. In 2x complement, there is, suppose, let's take a number. Suppose in 2x complement, let's take a number. Example 1, let's take a number. It's about 0, 1, 0, 0, 1, 0, 0, 1. I'm just taking a simple number 1, 2, 3, 4, 5, 6, 7, 8, and then let's put whatever we have memorized before, that 128, the thingy, though that let's put the number. Suppose 128, 64, 32, 16, 8, 4, 2, 1. So this is the main thing which we must memorize. I'm telling it 1, 2, 3 times because this number must be memorized. Now what we are going to do is just put the value 0, 1, 0, 0, 1, 0, 0, 1. Alright, so after we put this value, what we are going to do is just now, we're just now gonna do is just what can we do? Oh, I forgot. I will just remember it once again. So we are just going to swap it. Alright. So how we'll swap it is just 0 will be 1, 1 will be 0. Like this we are going to swap it. Alright. So 1, 0, 1, 1, 0, 1, 1, and then 0. This is the swapped now. So after we swap it, we are just going to add 1. Must remember, don't take it as a binary shift. Then it will get by binary addition, so you will mess up. So over here, let's do it. 1, 1, 1, 0, 1, 0, 1, 1, 0, 1. So this is the binary 2x complement. So this is the 2x complement. You must remember how I actually done this example. What I'm doing is just taking this number, then swapping it, then we are swapping it, and then after we swap it, after we have done the swapping, then we are actually like doing what? After we have done the swapping, then we are just adding it with 1, and after we have added the 1, then we are just getting the 2x complement. That's it. Just remember it, nothing else. So let's move on to the next one. We must remember the next one. Let's move on to the next one. So this is the sound and 2.1. We have 2.1. So this is the sound topic which we are going to, sound, image, sound, text and image. Over here I must read the syllabus. um, mm, read the syllabus, read the syllabus, what it has said. So over here I'm not going for the syllabus right now. We are just going to move to the main series. You must read it. Over here now, text to binary must be must do is just read and read and read several times. Read it from my notes or from the book, whatever, but just memorize it. Okay, I mean just read it, whatever happens. All right. Done using a tool called character set. Can be Unicode or ASCII code set, and ASCII represent a up to 8-bit binary. Unicode version, newer version with greater range 16-bit. Must memorize these things. Like must know the Unicode bit and ASCII code bit, binary bit, how much the value is stored, how much the bit is stored. Each character has a set of binary values, and Unicode requires more packet. So they will ask you to describe the text to binary about maybe about 5 points, 5 marks. So then you have to mention everything from here. Don't even miss out anything. Just mention everything. Just mention everything, whatever it written over. Alright, let's move on to the next one, which is about difference between the binary ASCII code and Unicode. Over is 7-bit and 8-bit. Whether there is 7-bit? No, ASCII code is not 7-bit. You must remember it's not 7-bit. Sometimes it's 8-bit too. You must also remember it. Write it here as 8-bit because there is no more 7-bit. There is 8-bit. It's an 8-bit binary bit. Alright, 128 characters. Oh, okay. More than allowed characters. You must write here more than allowed characters, a lot of characters, instead of writing this whole value. Is used to represent characters in English language. Obviously it's English language, and then presents around the world. Like you must read it several times so that you can actually like understand the flow, so that you can understand the flow. Less storage is required. Obviously it's less storage is required than the Unicode, then whatever it is. Then it presents up to 8. Like you must read to understand it, and there might be some questions about it. So I'm just going to give you some topicals so that we will be like in topical past papers when we are going to do it. That time we are going to actually like know about it. Image to binary, same thing. Just read and read the same. Read the things. Read the read to understand. One thing you have to in conversion to image to binary, you must actually like read this whole thing to describe the image to binary about 5 marks. Then take 5 to 6 points from here and then write it, because in computer science you must mention everything, otherwise you won't get any marks. You must actually like write everything, what you have in the memory, what you have in your mind, whatever it is. Just memorize the things. Don't memorize the things, just read and read. It will be automatically stored in your brain, whatever it is. If someone needs to memorize, they can memorize it, whatever it is. I don't have a problem. Sound to binary, the same thing. Just read and read so that you will be able to like answer the questions that are in 5 marks, 4 marks, 3 marks, whatever it is. Then you'll be able to actually like cope up with it. Now let's go for the storage thing. Let me read it too, like what it said actually. In the image is broken down into pixels, obviously, and by the computer, and then the image is a series of pixels. Obviously it is like you can write any of this. Like I must say it all over here. Like image is a series of pixels, An image can be broken down into pixels, whatever it is. Each pixel is converted to binary depending on its value, depending on its color, and which is then processed by the computer. Each color has its own binary value. Each metadata includes in dimension, date, and time. Then resolution is the number of pixels in an image. The color depth is the pixel used in the bit, and then file is the proportional to this, whatever it is told over here. Then sound of binary, we have actually read it several times. We must read it several times so that you could be able to store it in your mind, or whatever it is. Sound sampling is done to record sound waves and intervals. Sound wave is converted to binary to be processed by the computer, and then sound sample, and then part taken. And then this sound sample is beats power sample, loudness and pitch depends on the sample resolution. In the book there is some graphs and stuffs like that, but no need. Those are no needed. Just read the thing from the book and from my notes, so that you'll be able to answer 100%. Alright. Over here, this is the last topic. Just read the syllabus. If you miss anything or something, whatever, I have actually included everything in here. Read. So in file compression is the most important topic. I mean, most of the questions come from here, like maybe 60 to 40 to 20%. All right, like others are actually like basically like conversions, like binary to hexa, whatever it is, like those conversions, like last in the first part we have actually mentioned over here. Over here now, look at the thing. This read it so that you'll be able to understand it. Read every time. Read to understand whatever it is. Done to reduce file size, less storage required, less bandwidth required, less time taken for the transfer, quicker to upload and download. This must be easier thing. Then two methods are over here: lossy and lossless compression. In lossy compression, what you will have, find unnecessary and redundant files and to remove permanently. Usually for image and sound. For images, it can remove color and human can distinguish, can reduce sound depth and pixels, sound resolution. For sound, it can remove the sound that human can hear or soft sounds. It reduces sample resolution and sample rate. Just read it from the book or read it from my notes, whatever it is. Lossless compression, read it several times. Read. Alright, use compression algorithms to reduce the file size permanently without removing any data. Common in RLA, parallel encoding, which groups together repeating patterns and indexes them. For a text file, A is compressed to A like this thing, and the string for 4 A's and is followed by 3 B's and 2 C's, 1 D's and 2 A's. RLA is used in bitmap to compress sequence and same number. Let's go for the units of data. Data storage. Like just read these things or memorize it, so that you, when there will be some conversions they will come a lot. We are just going to do conversions in next few days. In file calculations, what we are going to do, we just need these two things with the data storage, like this thing. Must memorize it so that you will be able to understand. We will be able to answer. Just memorize this. Just memorize the formulas and stuff. That's it. So hope you like this video, and please subscribe and share this video, so that if anyone actually loves my video, then please don't forget to actually like it. And if you like my second part of the video, please also subscribe. I'll be very much happier. Thank you. Take care and safe. See you in the next video of chapter 2 in the next Friday.